In this video, we learn about the first fundamental principle of counting. It's called the principle of inclusion-exclusion. We shorten it by saying pi, which is convenient because we're in math, so we always like to refer to things as pi, if possible. So the principle of inclusion-exclusion is very important for counting. Okay, so here's where we start to count. So we're going to start with some notation first. So if we have a set S, little n of S, so n of S, is going to be the number of elements in set S. Okay, so when it's n of S, we don't actually care what's in S, we only care about how many things are in S. Okay, so let's see an example. So here I have the set A. A contains the letters M, A, T, and H. Okay, so letters of math. Okay, as individual elements. So there's and the universal set is all the individual elements of mathematics. So obviously the M is not repeated, the A is not repeated, but there's those individual letters. Okay, so then if I wanted N of A, so that's just the number of elements in set A, which we know is 4, because there's 1, 2, 3, 4 elements in A. Okay, so N of A is 4. Now in the universe, we could talk about the number of things in the universe. So I see that there's 8 elements in the universe. So that would be 8. Okay, but if we want the complement, so the number in A complement, we could find this by determining what A complement is. Okay, so A complement is going to be the set of everything in the universe that's not in A. So I'm going to just get rid of the things that are in A. So that's those 4 letters there. And then A complement is going to be the remaining letters. So E, I, C, and S. Okay, so that means that A complement is also 4 because there's 4 elements here. Okay, and it's actually not a coincidence that it's 8 minus 4, which is the number of things in U minus the number of things in A. Okay, which leads us to one of our first rules. So this is called the complement rule. So for set A with the universal set U, the number of things in A complement is equal to the number of things in the universe minus the number of things in set A. Because everything in the universe that is not in set A is going to be an A complement. So we take all the elements of the universe and we get rid of the ones that are actually in A, and we're going to be left over with the ones that are not in A. Okay, so that's our complement rule. So let's do another example here. So here I have the set A contains the letters A, C, E. Set B contains colors, so you can see where the commas are. Okay, so this is an element, this is an element, right? So we have 4 elements there. And set C contains some letters, some numbers. Okay, so the number of elements in A, okay, well we know that's 3. Okay, there's A, C, and E, so 3 letters. For B, there's 4 colors. So even though there's lots of letters in there, there's more than 4 letters, the elements are the colors themselves. So remember, elements can be anything. So here they're colors. So the number of things in B is 4. Okay, now in part C here, we want the number of things that are in A intersect C. So this is the number of things that are in A and C. So we might want to actually write out what is in A and C. So this is things they have in common. So we want to look and say, okay, well they have an A in common, and then that's the only thing. So it just has the letter A. That's the only thing that they have in common. So remember, this is the intersection, which is like the and. Okay, so that means that the element has to be in both sets. So here it's only A, which means the number of things in that set is just 1. Okay, now B intersects C. So you want to look at what do B and C have in common, and they don't even have form in common. So the B has all colors and C has no colors. So that means that B intersects C is the empty set, right? Because they have nothing in common, which remember you could also write with empty brackets, but don't combine those. So it's one or the other. So that's the empty set, which means that there is 0 elements there. Okay, so the empty set, this is the empty set, which means that it has 0 elements. Okay, now what about A union C? Okay, so this is where the principle of inclusion exclusion is going to come in. Okay, but let's actually compute A union C. So remember, this is the union, which is like the or. Okay, and we allow or both. So it's an inclusive or. So the way that I like to do these is I just write all the elements in one set. Okay, so these are the elements that are in A. And then I'm going to add in the ones that are in C that are extra. So I already have A, but I don't have B or 1 and 2. So these ones are the extra ones in set C. Okay, so then now I can see that A union C has 6 elements. Okay, so there's 6 elements in that set that we wrote out. Okay, now there's a way to compute that number without actually writing out the set. Okay, so that's where the principle of inclusion exclusion comes in. So this is for 2 sets. So if S and T are sets, then the number of things in S union T is equal to the number of things in S plus the number of things in T minus the number of things that are in S intersect T. Okay, so that's what we call the principle of inclusion exclusion. So let's just check that up above. Okay, so let's check for part E here. So the number of things in A union C should be the number of things in A plus the number of things in C minus the number of things in A intersect C. Okay, well we know there was 3 elements in A and 4 elements in C, and they had 1 in their intersection. So 3 plus 4 is 7, minus 1 is 6. So it did work out up here. So what happens is you're taking everything in A, and you're taking everything in C, and you're saying, okay, well, we counted some elements twice because some of them were in both sets, so these elements are the ones that were in both sets, so we're going to get rid of them one time. Okay, so then we've only counted them once because we don't want to have repeated elements in our set. Okay, so that's where the formula comes from. Now there's a, I wouldn't remember this as a different formula, but there is a case. So what happens when the intersection is empty? Well, that just means the number. So this, if S intersect T is the empty set, so if we're in the case below, then the number in S intersect T is 0. Okay, so the formula reduces to just n of S plus n of T. Okay, so that's only if the intersection is empty, so if they have no elements in common. Okay, so let's see this in action. So suppose at a Mother's Day tea party with 50 people, there are 25 people who have herbal tea, and 35 people who had black tea, and 15 people who had both herbal and black tea. And we want to know how many people had herbal tea or black tea, or both. Okay, so I'm just going to define some notation. So U, the universe, is going to be the set of people at the party, which I don't want that bracket, which means that the number of things in U is 50 because there was 50 people at the party. Okay, now H is going to be the people who had herbal tea. So then I know the number in H is 25. And I'm just using these letters to stand so that I know what they are. So you can pick whatever you want. But I'm picking H and B because of herbal and black. Okay, so this is the people who had black tea, which means the number of things in B is 35 because 35 people had black tea. And then the H intersect B is going to be the number of people who had both. And we know that that's 15. So this is had both types of tea. Okay, so that's what they gave us. Okay, now what we actually want is we want to know how many people had herbal tea or black tea or both. So that's the union. Okay, so herbal tea or black tea or both. Okay, this represents the union of the two. Okay, so we can do this using the principle of inclusion-exclusion. Okay, so using that, we know that this should be the number in H plus the number in B minus the number in the intersection. And I have all of these things. So that's 25 plus 35 minus 15. So we get 45 in total. Okay, so 45 people at the party had herbal or black tea or both. Which means, if we think about it, that because there's 50 people at the party and 45 had a cup of tea, that 5 of them did not have a cup of tea at all. So they had neither of these teas. And that's using the complement rule. Okay, so this is how we use it for 2 sets, but it actually can be extended to more than 2 sets. Okay, so I'm going to give you the case for 3 sets. And in our course, we're not going to go higher, but know that it can go up to as many sets as you want. Okay, so it can be extended further than this, but for 3 sets, so if we have sets R, S, and T, okay, they're just any sets, and then I want the union of all of them. So I want the number of things in R, union S, union T. The way that I find that is I would take the number of things in R, and I would add the number of things in S and the number of things in T. And then what I want to do is subtract off. So I've overcounted because some things are going to be in more than one of these sets. Okay, so then I've counted them 3 times when I don't want to count them. I only want to count them once. So what I do is I subtract the number in the intersections. So the number in R intersect S, and the number in R intersect T, and the number in S intersect T. But then I do have some elements that are in all 3. I could have some elements that are in all 3 sets. Okay, so they could be in all 3, but then I subtracted them 3 times because they're going to be in all 3 of these as well. So I need to add them back in. Okay, now in the next section, we're going to have a nicer way to sort of visualize this a bit. But for now, that's the formula. Okay, it's similar to the 2 set one, except we have multiple levels of intersection. Okay, so you add up the number in all the sets, in each set, and then you subtract the number that are in each 2 intersection, and then you add back in the number that are in the 3 intersection. And the extensions continue like this, so you're always adding and subtracting as you go multiple intersections. So that's the principle of inclusion-exclusion for 3 sets.